Okay, so in last class we have seen section modules with various shapes. Now today we will see problem related to the section modulus. Okay, a cantilever of length 2 meters fails when a load of 2 kilonewton is applied at the free end. If the section of the beam is 40 mm by 60 mm, find the stress at the failure. Okay, so a cantilever of length 2 meter fails when a load of 2 kilonewtons is applied at the free end. Okay, a cantilever beam. Cantilever beam means one end is fixed. One end is fixed. We will see a problem related to the section modulus. Okay, so a cantilever of length 2 meters fails when a load of 2 kilonewtons is applied at free end. Okay, so if the section of the beam is 40 mm by 60 mm, find the stress at the failure. Okay, so it is a cantilever beam, so one end is fixed and another end is free, there is no support. Okay, it is a beam with 40 mm by 60 mm and the load is applied at free end with 2 kilonewtons. With 2 kilonewtons. Length of the beam is 2 meters. Okay, so if you observe the cross section, width is 40 mm and the depth is 60 mm. Okay, width of the beam is 40 mm and the depth of the beam is 60 mm, right? Now the length, given length L is equal to 2 meters, that is, so 2 into 10 to the power of 3, we are converting into millimeters, that is 2000 mm. Next W, which is given in 2 kilonewtons, we can convert into newtons, it is 2000 newtons. Okay, so in the problem is asking to find the stress at the failure. Find the stress at the failure. Is asking the failure stresses. So we know the section modulus Z, and also when the section modulus Z is available, we have a formula M, that is equal to the stress, maximum stress into the section modulus Z, and we have to find the maximum stress here. Okay, we have to find the failure stress. Okay, now so we know the formula Z for the rectangular beam is for rectangular section, for rectangular section, Z is BD square by 6. Okay, so Z equal to BD square by 6. So B is given, that is equal to 40. Okay, B value is 40 into depth 60 square by 6. So 40 into 60 square by 6. 40 into 60 square divided by 6, that is 24,000 mm cube. 24,000 mm cube. Okay, so maximum bending moment for a cantilever at fixed end is M equal to W into L, which was shown at the fixed end. Maximum bending moment was shown at a fixed end. Okay, so that is W into L. So W is equal to 2000 and length L is also 2000. So that is equal to, so 4 into 10 to the power of 6 Newton millimeters. Okay, so now we know the max bending moment, and also Z. Okay, so using the formula, M is equal to sigma maximum into Z, so which was derived in section modulus. Here M equal to maximum stress into Z. Okay, so M equal to maximum stress into Z, and here we know M value and also Z value. So maximum stress is equal to M by Z, that is M is 4 into 10 to the power of 6 divided by Z value 24,000. So that is equal to 4 into 10 to the power of 6 divided by 24,000, that is 166.67 newtons per mm square. So this is the answer. Okay, so here we have find the maximum stress at failure. Okay, so when 166.67 is applied on the beam, it may fail. It is okay. So we will see another problem related to this. A rectangular beam, 200 mm deep and 300 mm wide. 200 mm deep and 300 mm wide is simply supported or a span of 8 meters. What uniformly distributed load per meter the beam may carry if the bending stress is not exceeded with 120 newtons per mm square. Okay, here section of the beam is given and maximum bending stress is also given. Okay, we have to find the load applied on the beam, and it is a simply supported beam. It is a simply supported beam, and the applied load is UDL, uniformly distributed load. Okay, so W per Newton meter. Okay, and the length is given L. So on two sides you may find the bending moment of WL by 2. So a rectangular beam of 200 mm deep and 300 mm wide is simply supported over a span of 8 meters. Over a span of 8 meters. What uniformly distributed load is carrying by this beam when the stress is not exceeding with 120 newtons per mm square. Okay, now the solution, if you see, the depth of the beam is equal to 200 mm, width of the beam is equal to 300 mm, and the length of the beam given is 8 meters. Okay, next maximum stress, which is equal to 120 newtons per mm square. 120 newtons per mm square. Okay. Okay, now let UDL is equal to W. Let UDL is equal to W. Okay, with okay, let UDL is equal to W Newton per Newton meter. W Newton meter. Okay. So for rectangular beam, the section modulus Z is equal to BD square by 6. BD square by 6. Here B value is 300, d value 200 square by 6, so which is equal to 300 into 200 square divided by 6, 20 lakhs, 20 lakhs mm cube, 20 lakhs mm cube. Okay, now maximum bending moment for a simply supported beam carrying uniformly distributed load is at the center of the beam, is at the center of the beam. Okay, and it is given by m equal to w l square by 8, m equal to w l square by 8. So w we don't know, l is given as 8 by 8. Okay, so that is w 8 Newton meter or 8w into 1000 Newton millimeter into Newton millimeter. 80,000 W Newton millimeter, we need to find W. Okay, now so using the equation m equal to sigma maximum into z, here m is given, that is 80,000 into W is equal to sigma maximum, which was given as 120 into 20 lakhs. Okay, 120 into 20 lakhs. So now W, required value W is equal to 120 into 20 lakhs divided by 8,000. Okay, so 120 into 20 8, so that is equal to 30,000 Newton meter, sorry, Newton per meter or 30 kilonewton per meter. 30 kilonewton per meter. Right. Till now we have seen the stresses in symmetrical sections, means either square or rectangle or the circle. So they are symmetric. But if so till now we have seen the sections in symmetrical model. Now we can see unsymmetrical sections like I sections, L sections, T sections, channels, etc. Okay, so there we can find the bending stresses. Okay, so bending stresses in unsymmetrical sections. Okay, so in case of a symmetrical sections, the neutral axis always passes through the geometrical center of the section. It always passes through the centroid. But in case of unsymmetrical sections, suppose an I section, if we consider one I section, it may be like this. Okay, or it may be a T section, or it may be an L section, or it may be a channel like this. Okay, if the structures are like this, then it is somewhat difficult to find the neutral axis where it is available. Okay, so these type of sections are called as unsymmetrical sections. We have to find the neutral axis. We need to find the neutral axis. Okay, the neutral axis does not passes through the geometrical center of the section for these types of sections. Okay, hence the value of y for the topmost layer or the bottommost layer of the section from the neutral axis will not be the same. Okay, so we have to find the stresses in the bending stresses in the beam with the bigger value of y. Means the maximum y maximum has to be utilized. Okay, so here the neutral axis passes through the centroid of the section. Hence, in unsymmetrical section, we need to find the center of gravity. First. Okay, we need to find the center of gravity. Once the center of gravity is known, the neutral axis may passes through that. Then we can find the y maximum. And then we can follow our problem. Okay, so in this type of sections, first we need to calculate the y. Okay, so how did we calculate CG here? Okay, so here we have a small formula to calculate the center of gravity with respect to x and with respect to y. So with respect to x, the center of gravity is a1 x1 plus a2 x2 plus a3 x3 etc. divided by a. Okay, similarly for y, it is a1 y1 plus a2 y2 plus a3 y3 etc. divided by a. Okay, Okay, so see here, suppose consider one T section, consider a T section. So divide this T section into two parts, A, B, C, D, E, F, G, H. So now we have two rectangles. Okay, here small a1 is the area of first rectangle, a2 is the area of second rectangle. Area of first rectangle is a1, rectangle 1, area of rectangle 2. Okay, and capital A is the total area of the T section, that is a1 plus a2 plus etc etc, a1 plus a2 plus a3 plus etc etc. Okay, similarly x1 is the distance of CG, is the distance of CG of the first rectangle from AB. Similarly, A2 is the distance of CG of the second rectangle from EH. So this is from AB and this is from EH, and etc etc. Similarly, Y1 is the distance of CG of the first rectangle from bottom of EF. Okay, from here we need to find the center of for the first rectangle. Similarly, Y2 is the distance of CG of the second rectangle from bottom of EF, Let us see a small problem. So find the center of gravity for the given diagram. Find the center of gravity for the given diagram. So top flange for the T section is 12 centimeters. Next width is 3 centimeters. Okay, bottom web width 10 centimeter and height is 10 centimeter and width is 3 centimeter. Okay, so for this diagram we need to find the center of gravity. So we can divide T section into two parts, say A, B, C, D, E, F, G, H. Okay, so this is 12 centimeter, this is 3 centimeter, this is 10 centimeter, and this is 3 centimeter. Now area of first, so this is first rectangle and this is second rectangle. So area of the first rectangle A1 is equal to the area of ABCD, that is equal to, so area of ABCD 12 into 3 36 square centimeters. Similarly, y1 is equal to the distance y. So here I am not finding the x, we need y only, y is important for us. Okay, so I am finding only y. Okay, so y1 is the distance of CG of the area A1 from bottom line, GF. Okay, so from the bottom line GF, we have to find it from the bottom line GF. So y1 equal to 10. So from here to here it is 10 plus half of the first rectangle, half of the height of the first rectangle, that is 3/2, which is equal to 11.5 centimeters. Similarly, A2 equal to 10 into 3, that is 30 centimeters square. Y2 is equal to the center point from the bottom, that is 10/2 is equal to 5 centimeter. Okay, here also we have to find it from GF. GF is the base, bottom line. So from bottom line it is 10/2, it is 5 centimeter. Now the formula y is equal to A1 plus y1 plus A1 y1 plus A2 y2 by capital A. Okay, so capital A is the sum of the total area. Capital A is the sum of total area, that is A1 plus A2 plus etc. Okay, so A1 36, A1 is 36 into y1 11.5 plus A2 30 into y2 5 by 36 plus 30, that is 36 into 11.5, uh, 414 plus 30 into 5, 150 divided by 66. So required value CG is 8.545 centimeters. 8.545 centimeters. Okay, so once we know the value of y, we can calculate the required stresses. For any type of section. Okay, for any type of sections like I sections, T sections, channel section and angular section. Okay, once we know the center of gravity CG, then we can find the stresses. Okay.